Okay, here is the last video that's going to wrap up all the new material for Chapter 2. So I'm on Section 2.6 on page 151, and I'm looking at Example 4. It says, an airplane is flying on a flight path that will take it directly over a radar tracking station. So we have a radar tracking station here, and we have this airplane flying on this flight path that's going to take it directly over this station. And there is a diagram in the book. The distance S is decreasing at a rate of 400 miles per hour. And S is the actual distance, the straight line distance from the plane to the station. And it is decreasing at a rate. So the rate that the distance is changing with respect to time decreasing, so it's negative 400 miles per hour. When S is 10 miles, so when the plane is 10 miles away, that's the rate that this distance is decreasing. It makes sense that this hypotenuse, this distance here, would decrease as the plane got closer and closer to the station. What is the speed of the plane? And then when you look in the diagram, this is 6, and they're calling this distance x. The speed of the plane. So we are trying to figure out the rate that the speed is changing. Speed is a rate, and so that would be dx dt, and that's what we're trying to find. We need an equation that relates all these variables. This is a right triangle, so we're going to use the Pythagorean theorem. A squared plus b squared equals c squared. So that's a great equation that we can use that relates all of these things. And let's see, when s is 10, we actually know what x would be. It's a 3, 4, 5 in disguise if you remember any of your triples from geometry, but that was a long time ago. So it's a 3, 4, 5, so it's a 6, 8, 10. If you don't remember it, then all you do is you plug in to the Pythagorean theorem and you find it. If s is 10, then this is 100. Subtract 36 from both sides and you get 64, so x is 8. So we know all of these things here now. And we'll go back to that equation that I had written down, because x is changing. As the plane gets closer and closer, this horizontal distance is changing. It would be getting shorter. And as the plane gets closer and closer, this hypotenuse distance would also change. So we've got x squared plus 6 squared. That vertical distance is not changing. That's how high the plane is above the ground. So to figure this out, we're going to do implicit differentiation, dx dt, plus the derivative of 6 squared is 0, equals, whoops, let me just erase this. Work up here. We're getting a little bit too crowded down here. So the derivative of x squared is 2x dx dt. The derivative of 6 squared, or 36, is 0. The derivative of s squared is 2s ds dt. We know what x is. We do not know dx dt. We know what s is. And we know ds dt is the negative 400 miles per hour. 16 dx dt equals 2 times 10 is 20, times 400, negative 8,000. Divide both sides by 16, and it's negative 500 miles per hour. That is the velocity or the speed of the plane. The negative just means that we're going to the left or we're flying west. Negative velocity is left or down. Positive velocity is up or right. So that would be our answer. I also thought that I should do a couple of the problems from section 2.6 that you've had so far. So page 153, I think I had to do number 5. So let's try it. A point is moving along a graph of the given function. Find dx dt at the rate of dx dt. Find dy dt for the given values. So 5 says y equals 2x squared plus 1. And they give you the fact that dx dt is 2 centimeters per second. And for a part, they tell us that x is negative 1. So we're going to do implicit differentiation. And we're trying to find dy dt. Plug in your negative 1 for your x and your 2 for your dx dt. And dy dt is negative 8. I'm also going to do number 11 for you. Okay, last one. The radius r of a circle is increasing at a rate of 4 centimeters per minute. That whole sentence was talking about how the rate of the radius was changing with respect to time. dr dt. The radius is increasing at a rate of 4 centimeters per minute. Find the rate of change of the area. Find the dA dt. Find the rate the area is changing over time. When r is 8 centimeters. Okay, so we've written down all the information they've given us and what we're trying to find. Now we need an equation that ties together a and r. And we're talking about a circle. So we know that area is pi r squared. So I've got my formula now. We're ready to just do implicit differentiation. Derivative of a is 1, dA dt. Pi is a constant. The derivative of r squared is 2r, dr dt. Let's plug in the things we know. We do not know dA dt. We have 2 pi times the radius times dr dt. That is 2 times 8 is 16 times 4 is 64 pi. So the rate that the area is changing is 64 pi centimeters per minute. Yeah, per minute. And sometimes they're going to give you a rate, and you're not going to know exactly what it is, but it'll be something like 8 cubic centimeters per minute. And if you're not sure what type of rate this is, like what variable to write down with it, sometimes the unit is going to give you a huge clue. What type of thing is measured with cubic centimeters? Volume. So that's a dV dt. And if they had said square, oh, this was square actually, centimeter squared because it's area. Yeah, if they had said square feet per second, you're not sure what this rate is. Square feet is a measurement of area, so that would have been a dA dt. So the units are helpful. All right, that's it for today's video. I'm not going to cover anything more in Chapter 2. This is as far as we're going to go. Wednesday we'll do a big review together.